Hey everyone, Michael Unger here with another episode of Ask an Astronomer. And as you can see, I am not at the Space Center, but I am in my home on the unceded territory of the Musqueam, Squamish, and the Tsleil-Waututh. And as always, we are here with our trusted astronomer, Marley. Hey Marley, how's it going?
It's good. I'm glad it's no longer 30 or 20 degrees anymore. It's too warm for too long. I had enough.
Yes, it was usually too warm in my apartment as well. And you know what that likely means. Yes, I did get COVID, but I'm feeling fine. The good news is that I got to reschedule my vaccine appointment for the same day as my flu shot. So maybe I'm
Nice.
saving time. Maybe I don't know. I
No,
love
mine's set up
efficiency.
that way too. I get my flu shot and my other booster at the same time. So I love that. Just hit me twice. Yeah.
Well, this show is not about vaccines. It's about astronomy. We've got some amazing stories to tell you all about today. If you're in YouTube land and you have any questions about any of the things that Marley's going to talk about, throw them into the comments or ask any question that you want under the universe. If you're out there watching on Facebook, you can comment on there as well, ask questions on Telus Optic. Won't be able to, but you can come on back to YouTube or Facebook and watch live. Now, Marley, last episode, 2 weeks ago, we were talking about DART, the Double Asteroid Redirect Mission. Now, for any of you that have not heard about this, NASA sent a spacecraft, smashed it into an asteroid, just like a fun video game. And a couple weeks ago, when this event happened, that was kind of it. It was really fun. We saw it close up, smash into it. But we knew that over time, NASA was going to get some data about the effectiveness because they didn't just do it for fun. They did it to, like the name says, redirect the asteroid. And you've got some news on how that mission went.
Yes, I do. Yay. So DART was a complete success. As it turns out, it was able to redirect the asteroid by a lot. So the asteroid Dimorphos, which orbits the larger asteroid Didymos. They hit Dimorphos, little moonlet asteroid, and their goal was to change its orbital period. That would tell us that they had moved it or knocked it into a new orbit. So its previous orbital time was 11 hours and 55 minutes. The threshold for it to be a success was a change of 10 minutes, whether that was more or shorter, but a change of 10 minutes. And the resulting orbital period ends up being 11 hours and 32 minutes. So they changed it by a fair amount. And so they have done a great job. But what I wanted to talk about a little bit was how they know that they changed the period of this asteroid. Because that was a question I had, was how are they going to know that? And
Yeah.
so it turns out they look at the total light of the entire Didymos and Dimorphos system. So this is a graphic that shows kind of what they're looking for. So you have Didymos, the larger asteroid in the center there. And then you have Dimorphos kind of orbiting around it. And as it moves along in its orbit, there are times when Dimorphos will pass over the front of the Didymos and then pass into its shadow. So this is a very highly magnified view. It's not this perfectly circular, nor is it this perfectly, split into half and half. But what we end up seeing is the combined light change. So that's where the graph comes in at the bottom here. The brightness dips slightly when either body is shadowed by the other. So when Dimorphos passes over the sunlit side of Didymos, there's a small dip in brightness because now part of the surface of Didymos is being covered. And when Dimorphos goes into Didymos' shadow, the dip in the brightness happens. And these happen with a set interval of time between them, right? Because it's an orbital period. These events happen after the same amount of time each time. And a lot of this they put into a very amazing graphic, which is a lot of info. So we'll take it piece by piece. So the top part shows the observations after DART impact to show the orbital change. So it's showing Dimorphos's eclipses, right? That's what that feature is called when it passes through. It's an eclipse. So prior to September 29th, we see the arrows, which represent the expected orbit of 11 hours and 55 minutes, and the golden yellow represents the observed. And prior to that, it's kind of like overlapped because we haven't changed anything. We don't expect to see a change. We are not taking any new observations. So they're at the same amount. That brightness when those eclipses happen are at the same time. The impact occurred September 29th. So this gray arrow is where we expect to see that dip, those eclipses to be. We expect to see them where this gray arrow is if we kept the 11-hour and 55-minute orbit. But what we see after the impact on September 29th is where this gold dip occurs. And it doesn't occur where that gray arrow is. Now it's offset by a bit. You can see it looks a little odd on October 2nd. That's normal. It takes a second for the orbit to figure itself out because we've smashed into something, but then it is able to kind of figure itself out and it becomes more and more stable. And so this gold arrow is showing the 11-hour 23-minute new orbit, and that's how they tell, by seeing where those little dips in light happen and measuring the time between them, and the time between them shortened in this case. So we see the bottom graph gives you a close-up of September 29th. This is the observed eclipse, or the dip in brightness from the 11-hour 23-minute orbit. And October 4th, we see it again, much further off than when we expected to see it for the previous orbit. So it's much better being able to see where the dip in brightness is compared to where it should be if we had kept the same orbit.
Okay, this is very cool. So if we were to think of this in practical terms, so we can now see that the orbit has been changed, by what we're talking about here, roughly about like 25 minutes or so. But I guess practically speaking, if say an asteroid was heading towards us, what does 25 minutes equate to, I guess, in like spatial orientation?
Well, depending on how fast it's moving, that can be a very great speed, right? If something's going, hundreds of kilometers an hour, that's even more kilometers a minute. A change of 25 minutes is enough to, I think it's 32. I think I miswrote the time before, but a change of that time is like between possibly hitting Earth and missing Earth by a fair margin. So it's a big deal. Yeah,
that's good. We don't want to hit Earth. That's the main goal here. We don't care about the numbers. We just care about it missing the Earth.
Let's like the bigger conversation with the whole DART mission can something like this even work? And it can actually work very well, because we knocked it out into such a different orbit by such a large margin than what would have been considered successful. It bodes well for future experiments and using this as a possible technique of, asteroid and planetary defense.
Okay. Well, this is very cool. So what now with this mission? Like I said, once it smashed into it, that was the really exciting part of the mission. Now we're making lots of observations. Is the quote unquote, is the mission still ongoing? Like, what more do they want to find out from it?
Well, I mean, they're not just going to stop looking at the system. Like, it's still very interesting. There's still lots of things to learn, as well as looking at it, over time. What I'm particularly interested in is all the debris, because if you watch the last video find the photos that were shown, there's this huge amount of debris that comes off of the asteroid. And a lot of it ended up just falling back down onto it. But my interest is like, well, what is that made out of? Like, what is that stuff? So I don't know, like, more things to look at. There's more information about like how the impact like occurred, how it impacted the actual features of the asteroid itself, and just other things to know, as well as just continuing to monitor the orbit to see what happens. But the mission is kind of like done. Like, they did it. It's
right.
There's not much else to do after that.
Okay.
It's all like gravy, I guess.
Awesome. Well, I like gravy as long as it's vegan gravy. I'm not so much of a meat eater, but we've got some more pictures, some more news stories that have come out. Marley, you've been talking about this amazing picture that has come out from the JWST, the Pillars of Creation, which is a famous picture that was taken by the Hubble Space Telescope. There is now a new updated version of this fantastic picture called the Pillars of Creation, and it is just stunning.
Yeah. So this was the one that I was like, oh, this will be one of their first 5 images. And then it wasn't. And I was like, what a bad choice. But okay. And now it's finally here, and I'm so happy because I've really wanted to see this in the infrared, because this is the Webb image, but in the Hubble image, like, you can't see any of this. Essentially, you just see the gas, like the dust structure of like the hand. It looks like a hand to me. And so it doesn't, I don't know.
Wait a minute, but you always say that you can't see pictures, and now you're saying you can see a hand.
Well, that is a hand. I don't know what to tell you. That is pretty clearly a hand. And so in the Hubble image, like all of these stars, like in this area, a lot of the ones in here are just completely like blocked out. Like you can't see any of them, nor can you see a lot of like all of this behind here, like all the background features, all the background stars, because it's inside of a nebula. It's all of this dust and gas and material that block out visible light. But infrared light is able to pass through pretty much just fine. And so seeing a infrared view of it is just like supremely exciting. And Hubble took an infrared view with its camera when it still had one, and it was good. But this is just like amazingly better. And I think if like someone had been near me when I first saw this image, I would have like broken their eardrums. Like I just lost. It's so cool. I like screamed so loud. It's such an amazing image. It is so. It's my phone wallpaper now. Anyways, so to describe like what's going on here is that these are all newly formed or very young stars in the image. So typically when we look at a Webb image or the Webb images we looked at in the past, these stars here with all of these diffraction spikes are typically stars that are in the foreground. Like when we're looking at galaxy clusters, for example, stars with those diffraction spikes are usually in the foreground. These ones are not in the foreground. They're just exceptionally bright. They have the 8 diffraction spikes, especially the red ones. Those are stars that are young and very bright, and they're bright enough to cause that diffraction that we see with the spikes that it has. We also have like closer in, like the next image kind of shows it a bit better, but we have like these wavy lines on the edges of the pillars. It looks a bit like lava. Those are ejections from stars that are still forming. So stars that have not yet become stars. They're still kind of figuring themselves out. And those really young stars sometimes shoot out supersonic jets out of like the poles, like the North and South Pole. And those jets will interact with material around them, and like the thick pillars of gas and dust in which the star lives. And so that causes like shocks, kind of like when a boat like goes across the ocean, you get like those waves coming out. It's similar to that, except it happens in the gas and the dust. And so you get these fun wavy patterns coming off of the gas and dust seen in the gas and dust. And the stars that do that, like these lava sections where those young stars are only estimated to be a few 100,000 years old. So really like the very, very young stars, haven't been around for very long. And the other thing about this image that I really want to highlight is that sometimes when we look at a Webb image and there's all these things in the background, I'm like, oh, those are galaxies. There's no galaxies in this photo. These are all stars, because the interstellar medium in this nebula, like gas and dust, blocks the view of the light we would see from the galaxies. And so how did they explain it? In their press release, they explained it as being in a very brightly lit room and trying to look outside a glass window. It like your room is so bright that it kind of blocks the light from outside, and you're just illuminated in this very bright room. And that's essentially what's happened to Webb in here. The interstellar medium is in the way that gas blocks the view, but also the pillars of creation and the stars themselves are so bright that it's like preventing, like it outshines what's behind it, essentially. So it's amazing picture.
Yeah, very cool. And I think like one of the reasons that the Pillars of Creation is such an iconic image is that those pillars, right? Like they're long, they're skinny. It looks like something, that we can imagine in like, say, like if we have like a tub and we throw in some dyes and we're sort of like seeing sort of like the different colors kind of like form these little gaseous regions. It feels familiar, even though it feels so far away, as opposed to, lots of other nebula pictures that just kind of like look like clouds. Like if you were to see clouds like this in the sky, you'd be like, whoa, that is wild. What is going on with those clouds right now? It's very, very unique.
No, it's a very unique structure. And that's why I think it's so, because it's so easily recognizable, because it looks so odd compared to other nebula that we see. But it's just like the best picture. So this one, I flipped it because I wanted to try to get everyone to see how much detail is in this image. And if you go to their press release, the Space Telescope Science Institute press release of the image, you can like zoom in, and it is just phenomenal. It's so cool. I'm like, I love this background that I have, but I'm like, what if we what if we swapped it? We put that one up.
Yeah, very cool. And even just like flipping it like that, like totally changes sort of like where your eye goes. Like often with a picture like the Pillars of Creation, we quite often only see it in one orientation. So I think this is really cool to kind of now look at the exact same thing with a completely new lens and literally with a new telescope.
Yeah.
This is very cool.
This is my favorite feature. This red part. That is just the coolest. Look, it's so awesome. There's all those little stars in there. Anyway, yeah. Great. Finally happy I have this picture now. I've been waiting a long time for it. Thank you, James Webb team. Yep. So
very cool. We've got one more story to get to, but we actually got a question on Facebook from Martin Bancroft. If we go back to the Didymos system.
Okay. Which part of it?
What orbit change would you expect from a billiard ball-like collision if Didymos was a hard body, and how much less was the actual change?
Okay, so if Didymos was a billiard ball-like collision, okay, wow, take me back to physics 12. Billiard ball-like collision if Dimorphos, the one we hit, was a hard body, and was it the same change? I have not done the math, but it wasn't the same amount as you would expect from that kind of question, like a kinematics dynamics question, because Dimorphos is in orbit around Didymos. So that also affects how much it's going to change, because you have to deal with that gravity influence, as opposed to just hitting a still object. Like it's also moving. And so that had to be considered as well. And so it would probably be the change, I would think, would be less than doing just a straight, solid still object being hit by a moving solid object. It would be a less of a change, but still a good change based on what they were trying to do.
Yeah. And I guess, do you think a mission like this, like now that they've proven the concept, are we going to see more missions like this, perhaps from other space agencies?
Maybe, like, part of it is like this system was kind of like, oh, perfect, right? Because it's nowhere really on any way to come near us. It happens to have a little moonlit asteroid that we're able to figure out the orbit of. That's a reasonable time, and it's of reasonable distance to us, right? So there was like a lot of factors that went into picking this system. So they'd have to find another good system to do it with. But I would not be surprised if more missions started coming out similar in scope to what this is.
Yeah, and it certainly seems like Earth defense as like a category should be a worldwide effort.
Yes.
And it is really cool that this particular mission had other space agencies involved as well, including the Italians. Martin's follow-up question was that those Italian CubeSats that were trailing DART were taking images. So his question is, do we have any idea when those images are going to be released?
Oh, they've already been back, actually. Some of the images have already come back from Leica Cube and also from Luke and Leia. Like those are the instruments on board. They've already sent back images. If you go to the DART mission website, they have images that have been released from those two. I'm not sure if they've released all of them, but they've definitely released the ones that, because they were observing when the impact happened. So they have those ones. Those images have been released. So you can see those.
Okay, very cool. And of course, our second big story was about the Pillars of Creation. And regular watcher Harry asks, Pillars of Creation, isn't it a misnomer because it's not a singular structure? Are we seeing it as a collection that has form, but everything is all separate? So kind of like trying to piece out the words that we use, of course, pillars, nebulas. Is this one big structure or more kind of like an optical illusion?
So the Pillars of Creation themselves are part of a larger thing called the Eagle Nebula, right? So the Pillars of Creation got its name as like the photo from Hubble Space Telescope, right? Is where that name first comes from. And so the pillars it refers to are like here-ish, right? These big ones up here are the Pillars of Creation from like the claw. Is that what would be? And it's part of the larger collection of gas and dust of an Eagle Nebula, which is like more than everything in this image. It's actually quite zoomed out, but you can kind of make out where the pillars would be. If you go to like the Wikipedia page for the Eagle Nebula, the photo that's there, that is, it's like pink. The very bottom of it is where the pillars are. They're like kind of reaching up. That's where that is. And so what you're seeing is a collection of pillars. Yes. So these are the pillars, and this is like another structure, and this is another structure. But from our view, it looks like they're all kind of all together.
Right. So essentially, like this region, this giant nebula, is a region where a whole bunch of young new stars are being born. Is really what this region is, which makes it different from other areas of the galaxy, right?
Yeah, it's just like it's number one, looks very cool, and number two, has a lot of things going on, which is what makes it interesting. But the pillars themselves are like just the very tippity top. This is considered the Eagle Nebula part, but it looks better altogether, I guess. But yeah, it's different things all kind of in one spot.
Awesome. Well, we've got one more story for you folks before we wrap up this episode, and that is a detection of some GRBs, which are gamma ray bursts. If this is a new terminology for you, Marley, what is a gamma ray burst?
Okay, what is a gamma ray burst? I will quickly jump to that slide. Okay, a gamma ray burst is a term we use to describe the brightest explosions in the universe, some of the brightest explosions of the universe that we see. Astronomers aren't very creative with names, and so a gamma ray burst is a burst of gamma rays. That's what it is. But they're very short-lived. They don't last very long, and they signal the creation of a new black hole, essentially. And there's two different types. So there are the short duration ones, which last shorter than like 2 seconds. Typically, they're in millisecond range, right? Don't last very long at all. Those are less common. They tend to be a bit dimmer, and they have more of the highly energetic gamma rays involved in them. And it looks like the conversion of energy into those gamma rays will decrease as the burst goes on. We think that those short-lived ones come from compact object mergers. So a neutron star combining with another neutron star, or a neutron star combining with another black hole, right? So these are often associated with the creation of a new black hole, or two large compact objects combining to do that in the terms of short-lived ones. In the terms of long duration ones, those one last between 2 seconds and several minutes, so a bit longer. They're much brighter, and they have less hard gamma rays. Their energy conversion appears to remain constant. It doesn't like decrease as the burst goes on. It's like at a set level. And we think that those long duration ones, that some of them come from the core collapse of massive stars in something called a hypernova, which is a word to describe a very energetic supernova. So the end of a star undergoing core collapse, where its inner region is literally collapsing in on itself as it has run out of things to power fusion, and it is now collapsing under its own gravity. Those happen in massive stars over 30 solar masses, and they collapse to form a rotating black hole emitting twin energetic jets, right? Or so we, think is what happens. I don't think we've ever seen one. Surrounded by an accretion disk. And that core collapse in that star will happen so fast, like the intersection will collapse down into a black hole so fast that the outer parts of the star, those outer layers, don't know what's going on. So everything collapses and those outer layers are still there. And so once that collapse happens and those jets form, the outer layers of the stars are like exploded and ripped apart by those jets and the winds formed from the newly formed core collapse event. And so the accretion disk is blown away, and the shock wave from that, smashes into these outer layers of the star. The jets burst through the outer layers of that star, all that material, and you get a huge gamma ray burst from that. It's a highly, highly energetic event. And so you'll see gamma rays. The formation mechanism still a bit up for debate, but this is what we think causes those long duration ones. So whatever the mechanism it is, the gamma rays are beamed into a long, narrow cone along the direction of motion of the jet, which makes them hard to see because we only see that burst of gamma rays if that jet is pointed towards us.
Okay. We've got definitely got a few questions coming in on this. This is a really cool topic. Now, Marley, just to clarify what we're talking about here, when we talk about gamma rays. Now, and I see Pride is also sort of like answering the question as well. But gamma waves are on the light spectrum on the very extreme end of it, and that's what you're talking about when you say gamma rays, right?
Yeah, yeah, the highest energy of light that we have. Yeah.
So very highly energetic light be very dangerous, you know, if these hit us, I'm guessing. Is this kind of like where this story is going, or are gamma rays
No.
dangerous?
I mean, they're not good, but that's not where this story was going at all. No.
Okay.
Sorry. No, no, no. I'm so sorry if I cause any undue stress. No, it's this. No, 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 no. It's just cool because we saw a really bright one. That's all that
Okay.
happened.
Okay. And then Harry follows up when seeing, observing a burst of time so short, under 2 seconds. How is it possible for it to be detected on the radar or scope?
So we have gamma ray telescopes that orbit Earth all the time, or in our orbit. The Fermi Gamma Ray Telescope is one of them, and they are just constantly looking. And when gamma rays hit them, they just automatically start recording that data. So that's what happens with Fermi Telescope. There's a couple other ones that do the same thing, but they have to be in space because gamma rays won't reach us on the ground. Our atmosphere protects us, so it's not a problem. But so they will be hit with them and then they'll look. And how do we know they've happened is because we look for something called an afterglow. So we combine the detection of the gamma rays from the space-based telescopes, who are just kind of like in limbo waiting to be hit by something, with the combine them with the afterglow that we can see from some of them. And we typically see more of an afterglow with the long duration ones, which is what this image is. So this image just looks like stars, but the gamma ray burst is that red thing there. So that is the aftermath or the afterglow of a gamma ray burst. This was taken by the Gemini South telescope, and it's a combination of optical and infrared data. So we don't see the afterglow in the gamma ray. We see them in kind of everything else. Typically X-ray, we see them a lot in the X-ray, but we also see them a lot in the infrared as well. So we can look at that area of the sky where the gamma ray came from, where the gamma ray burst came from, and use our other telescopes on Earth or in space to look at the afterglow, because these gamma ray bursts are still observable at the less energetic wavelengths. They, are not, the gamma rays come, we know about them, and then we look and kind of see everything else as it goes on.
Okay. So in terms of like how astronomers do this kind of work, is there like known places where the gamma ray bursts usually come from, or are they kind of looking at a certain big region of sky? They see a potential gamma ray burst coming from one part of the sky, and then that's where they kind of hone all their observations to.
Yeah, so it's kind of like luck of the draw. Like if you're in the right area and the gamma rays have hit you, and that gamma ray jet is now pointed towards Earth, is when it'll hit us. So this is showing from the Fermi Large Array Area Telescope data, and it's showing the sky in gamma rays where it was looking. And they're very, very energetic. The brighter means the stronger the gamma ray signal is. The glow that you're seeing in the mid plane, like this feature here, is the Milky Way. So that's the Milky Way in gamma ray. And the gamma ray burst is that bright thing that outshines the entire Milky Way. So there were a couple of telescopes up there, gamma ray telescopes up there. And I think one of them got hit and it was too high of a signal for it to be able to, it saturated all of its detectors. And so it pinged the next one over. And so basically all of the gamma ray telescopes and got a ping of hey, we're being hit with something. And that was on October 9th. And so after that, the X-ray telescopes looked at that area, and then telescopes on the ground looked at that area to see what would be going on. Just on October 14th was when Gemini South looked at it. And so the gamma rays get hit first, and then they tell everyone else, look in this area of the sky, there's going to be something neat. And then everyone does. Very
cool. Well, there you go. Gamma ray bursts. Such a diverse show we had here. We talked about DART asteroids. We talked about the pillars of creation, and now gamma ray bursts. Thank you, Marley. Thank you all for all of you watching in YouTube land, even Facebook land. I got our first official question from Facebook. We are live every second Thursday. We'll be back again in a couple weeks. We have an event in person. If you haven't got your ticket yet to meet Joshua Kutrick, he's going to be on site with Marley tomorrow. You can go to our website, spacecenter.ca, to reserve your spot and hang out with him, talking about going back to the moon. Will it be Joshua? Hopefully, he's ready to go. He's going to be in his blue jumpsuit. They're always in their blue jumpsuits. I feel like they're all like at any moment they could be ready to go to space.
That's their uniform. Come on, they gotta be the astronaut. Yeah.
Yeah, and also it's a return of 19 plus events next month. We are going to be bringing Cosmic Nights back, the official Cosmic Nights with beer and wine on site. We also have the online version as well, which is quantum cosmology. Our former astronomer Rachel Wang is coming back, and Marley and Rachel are going to be delving into a very cool subject, going back to the beginnings of time and how quantum cosmology, well, specifically quantum gravity, helps us understand the beginning of time. So those are going to be on sale very soon, so check our website out for that. But like I said, we'll be back here on YouTube and Facebook in 2 weeks at 2 p.m. Pacific time. We will talk to you all then. Take care.
Bye, everyone.